Hello everyone, thank you for joining today. We are going to explore something absolutely foundational to the rapid expansion of AI, the network fabric. Before we dive in, let me quickly introduce myself. My name is Nazim Khan, and I'm a solutions engineer at Cisco on the data center and the AI infrastructure team. My job is to make sure the solutions we build align with our customers' real business needs. I've been in the industry for over 23 years, working with companies like Motorola, Quest Communications, and Cisco. I hold a dual CCI certification and have delivered multiple sessions at Cisco Live across the US and Europe. Now, why are we here today? Because we are living through one of the biggest infrastructure shifts in the history of computing. Every organization is racing to build or consume AI models. And the interesting part is this: the bottleneck in AI isn't just the GPU speed anymore, it's how fast those GPUs can talk to each other. You can buy the fastest GPU in the world, but if they are connected through a slow or congested network, it's like driving a Ferrari in a traffic jam. All that horsepower completely wasted. So, in the session, we'll look at how Ethernet, the same technology that powers the internet, has evolved into a high performance fabric for scalable, secure AI training and inference. Here's a roadmap for our session. We'll start with the silicon building blocks, the CPU, GPU, and the DPU. Then we'll look at the different types of AI clusters and the specific networking requirements for each. The core of our discussion will be on network architecture, focusing on RDMA, Rocky V2, and congestion management. Finally, we look at the future with the Ultra Ethernet Consortium and discuss security. Let's start by breaking down on what actually sits in a modern AI server. It typically contains three major processing units: the CPU or the central processing unit, which is the brain of the AI system. It manages the operating system, orchestrates data loading, and handles all general purpose tasks. Think of it as the conductor of an orchestra, making sure everything stays in sync and harmony. Next is the GPU or the graphics processing unit, which can be termed as the muscle of the AI system. This is where the heavy lifting happens. GPUs excel at massive parallelism, performing thousands of matrix multiplications at once. In AI clusters, GPUs are the most expensive resources, and everything about the network is designed for one purpose: keep the GPUs busy. If a GPU is waiting for data, you're literally burning money. Finally, the DPU or the data processing unit is the traffic controller of the AI system. As network scales to 400 gig and 800 gig, processing packets eats up CPU cycles, what we call the infrastructure tax. The DPU offloads that tax, handling encryption, packet inspection, and routing so the CPU and GPU stay focused on their workload. Thinking of DPUs as a personal assistant, making sure the main performers can shine. These three components together form the backbone of modern AI infrastructure. So, what is an AI cluster? Isn't it just a rack of servers? Essentially, it is an interconnected network of high performance GPUs acting as a single supercomputer. The network here is not just the plumbing, it is part of the compute fabric. If the network slows down, the entire cluster stalls. This brings us to collective communication. In standard networking, A talks to B. In AI, a whole group of GPUs need to exchange data simultaneously to function as a unit. During training, every GPU calculates a gradient, and they must all share that data to update the model. We use topology aware algorithms like rings or trees to ensure this happens instantly. If this synchronization lags, training time explodes. Now let's distinguish between the workloads. Training is where the model learns, it uses massive data sets to teach the model patterns. It's like teaching a robot to read, walk, dance, whatever the robot was built for. Inference is the application phase. This is when you use the trained model to make predictions or generate text. It's like asking that robot a question and getting an answer. Let's look at the specific requirement for each of these clusters. As shown in the table, the bandwidth. Training requires a high node to node bandwidth because of that gradient synchronization, which we talked about. In inference, it's the bandwidth requirement is relatively lower. The key metric for the training and the inferences for the training, the key metric is how much time it takes to train the model. For inference, it is about latency and high availability. So basically, if you think that you're building a robot, how much time it takes to build the robot and how much time it takes to train the robot so that it can perform the task which it's intended for. Inferencing is just like executing the robot. So basically, the end user commands the robot to walk, dance, or whatever the purpose it is built for to execute the purpose it is built for. Training happens offline, like when the robot is being built, it is trained, it is not available for the user. It's still being manufactured by the company or the system which is developing it. Inference is online, right? The robot is available for service whenever it's required. From an infrastructure requirement, training clusters are massive. They're like centralized networks because they require a lot of bandwidth. And the more resources they have, the lesser time it takes to train a particular model. Inferencing clusters are often small and distributed, something similar to what we have been using in our data centers. The regular networks, what we have been using in the data centers, those could be used as inferencing clusters. So, with those differences in mind, let's talk about what it takes to build a network that supports these workloads, specifically a lossless network fabric. This is where technologies like RDMA, congestion control, and specialized architectures come into play. To get the performance we need for training, we use RDMA or remote direct memory access. Standard networking is too slow because data has to pass through the CPU. RDMA allows the NIC to transfer data directly into GPU's memory, bypassing the CPU entirely. This gives us the low latency required for a lossless fabric. I often joke that if humans had RDMA, you could just sit in the room and by the end of the session, all my AI networking knowledge would be copied into your brain instantly. But for RDMA to work, the network must act losslessly, meaning no packet drops, even during spikes or congestion. This requires careful planning around buffers, queues, and traffic engineering. Now, we may say we are using RDMA as a technology. How about the physical network for AI? Here's the high level topology. We typically split the network into two, which is the front end network and the back end network. The front end network is your standard Ethernet network, which you use for your storage, out of management, user access, just the regular data center which you have been using. The back end network is the place where the magic happens. This is a dedicated high speed GPU to GPU fabric. So, any model you're training here, any robots you're training here, it has to happen in the backend network. It is purpose built and it carries only compute traffic. The GPU gradients, which you talked about, the activation, the model parameters, all of that happens in the backend network. And of course, since the backend network uses RDMA because it involves GPU to GPU communications, it has to be lossless. Because if any packet drops, the entire collective operation or the collective communication we talked about between the GPUs will stall or has to restart. For the backend network, which runs RDMA, we have two choices in terms of technology or in terms of system infrastructure. Either we could use InfiniBand or we could use Ethernet. InfiniBand has been used in high performance computing. It's a standard, but InfiniBand is proprietary. It is fast, it has better latency as compared to Ethernet, but it is proprietary and all its component, all its element, the infrastructure to build up an InfiniBand a cluster, it's expensive. RDMA is natively supported on InfiniBand. Like it does not require any tweaks or adjustments to run RDMA over InfiniBand. You can just directly run RDMA over InfiniBand as is. However, when you talk about Ethernet, so Ethernet, as we know, is a best effort technology. Basically, it's not lossless. RDMA requires lossless, what we have been talking about. And what we have done to run RDMA over Ethernet is we have developed some industry standard or particular protocol, which we're going to talk about in the upcoming slide. And then we also have to kind of configure or make the Ethernet with certain congestion mechanism to make it at on par with InfiniBand without compromising on its features. So Ethernet as such we know is a standard being used widely, very popular. Most of the folks out there know how to operate Ethernet, the switches, the optics, all the infrastructures are quite standard, and we can run the entire backend network over Ethernet. We don't have to change anything except for the part where we have to tweak the RDMA to how to use Ethernet. So we have to customize Ethernet for RDMA, and nothing is non-standard. Everything is quite a standard procedure. So the big question here, what it takes to get Ethernet on par with InfiniBand. So the answer is Rocky, which is nothing but RDMA over converged Ethernet. What we do here is we encapsulate RDMA inside an Ethernet frame. We started with Rocky version 1, which was only limited to layer 2 domains because it did not have a UDP IP header. Then that was slowly upgraded to Rocky version 2, where we added the UDP IP headers. RDMA would be able to route across layer 3 networks. So this is what allows Ethernet to scale AI clusters across racks, rows, and entire data center halls. So let's talk about more about Rocky V2. With Rocky V2, GPUs still use RDMA, but now the RDMA packets ride over Ethernet. The NIC can place data directly into the GPU memory without involving the CPU kernel, which cuts latency from microseconds to nanoseconds. This is the magic that makes Ethernet a serious contender for AI networking. Of course, using Ethernet introduces one challenge. RDMA assumes a lossless network, which we talked about, and Ethernet is best referred. If the buffer fills up, Ethernet drop packets, but RDMA cannot tolerate drops. So we introduced two mechanisms here, starting with the ECN, which is the explicit congestion notification. ECN does not drop packet. Instead, it marks them when the switch starts to build queue pressure. The endpoints then slow down based on those marks. This keeps the network stable and predictable, exactly what AI workloads need. The second mechanism is PFC or priority flow control. PFC pauses traffic at specific priorities when congestion occurs. This gives us per priority lossless behavior, even when multiple traffic types share the same links. Proper tuning of PFC, the headroom, the pause thresholds, and the queue management is critical to deploying Rocky V2 successfully. Looking ahead, the UEC or the Ultra Ethernet Consortium Initiative is an industry group optimizing Ethernet specifically for AI. They are developing standards for better congestion control, lower latency, and broad interoperability to replace proprietary solutions completely. So what we are seeing here is a UAC because we know that Ethernet in its own form cannot be used for the backend network. What we discussed about how we use Rocky V2 and how we are using congestion mechanism. So the goal of the Ultra Ethernet Consortium team is to ensure that we develop a standard Ethernet or a modern Ethernet, what we call it, or what they call it as Ultra Ethernet, which will work flawlessly for building AI backend networks. Performance is critical, but so is security. AI introduces new attack surfaces that traditional tools don't always cover. Some key risks included here, like I put it on the slide, is data poisoning, model extraction, privacy violations, insider threats. As AI systems handle more sensitive and proprietary data, securing the pipeline just becomes an important as accelerating it. To address these risks, we rely on many core strategies, which is like encryption of data in transit and rest, secure designs, continuous monitoring. We monitor the AI network continuously to discover any anomalies in traffic flows or any anomalies in behaviors of the users. And then access control, which is all very important in aspects of securing a network. So these guardrails ensure AI workloads remain secure even as they scale dramatically. Talking about DPUs, DPUs play a huge role here. They enforce these security policies like encryption and isolation right at the server edge, offloading the work so the GPU can focus 100% on training. They also help with model partitioning by managing data movement efficiently. Let's bring everything together. What we discussed so far is scalability aspect, how we are making AI networks more scalable. So AI is moving from a single server to massive clusters, like we talked about how we require massive amounts of GPU to cater to the AI demand what we have. So the network must also scale with it. We discussed about performance, how Ethernet with the Rocky V2 can provide the high throughput, low latency fabric AI workloads require. Also, we talked about the UEC or the Ultra Ethernet Consortium initiatives where they are trying to develop Ultra Ethernet, which would work flawlessly with the AI backend network. And if you get the network architecture right, you can build a system that's fast, secure, and ready for the future of AI. Thank you for your time. I hope this was informative and I wish you a great conference.